now?
Huh? What?
You're really pushing the ability of my brain to think, so.
That's kind of what I get paid to do.
I appreciate it, it's just really pulling it to
You
me.
mean the thin lens equation?
My apologies.
Yeah, but there was the one
You don't have to
problem where
follow
it was
them.
like.
Well, I'm trying to be
Magnification
polite.
of 2 and then. So.
So,
I don't know.
it's rare that I try to be polite
Or
and
no, you have to
embrace
go at the focal
this.
length, you,
Okay.
and then it's what you magnification of 2 and you have to find the.
All right.
And
So, let's,
I was explaining that.
okay, let's chit chat. So, when you look at these equations, and there's a fourth one for UI, which is K Q1, Q2 over distance, okay? You have to pay, more so than about any unit that you have to deal with, you have to pay attention to the units because of the fact that these are counterintuitive. If you look at the equation, velocity equals distance divided by time. Oh, that makes sense. It's meters divided by seconds. That's intuitive. I get velocity. That's meters per second. But to look at this and go, oh, voltage equals ED, well, okay, whatever, right? Doesn't make, it's not intuitive. Or E equals KQ over R squared, whatever, okay? And then, better yet, you can just reach that point where you just use FAC and go, okay, whatever. So, here's the point. None of these equations, when you look at them, really make sense unless you pay attention to the unit. So let's start with this idea. Q is going to be a measure of what? Start with that.
Coulombs.
Charge.
Measured in coulombs.
The fact that there was any moment of hesitation in that question causes me pain. Okay? I know. Okay?
Like a really low pressure.
Blame it on the low pressure system. So any Q is going to be coulombs, right? Any electron or proton has what value of charge?
You said what now?
Any electron or proton has how much charge in coulombs?
1.6 e to the negative 19.
1.60 times
E to the negative 19 coulombs.
negative 19th coulomb, which is very small, right? But they're all the same. Every proton, every neutron, or excuse me, every proton and every electron we studied has the same amount of charge, has the same amount of mass. It's a cookie factor. It's the ultimate one. So, if you look at this in terms of the value of K, which is this constant, what are the units for that value of K? K is always going to be newtons
Meter squared.
over
Coulomb squared.
Coulomb squared. Okay, cool. Now, if you look at this one, where you have newtons, meter squared over Coulomb squared, times coulombs divided by meters squared. Oh, the meter squared cancels out, or it's just over, over, I'm going to lose one of those, so I have newtons per coulombs. So your electric field is going to be in newtons per coulomb, which is a force per unit of charge. So this is why this makes sense. So your electric field is going to be newtons per coulomb. So now when you go to ED, voltage equals ED, then you have newtons per coulomb multiplied by a distance in meters. Well, then you have Newton meters, which is joules. So that works out to be joules per coulomb. So voltage is joules per coulomb. It's the amount of energy there is per unit of charge. So for those of you that just got done with AP chemistry, we just got done talking about voltage as applied to voltaic cells. Like your battery, typically in your car, is a 12-volt battery, which means it has 12 joules per coulomb of charge. Okay. When you look at force, K, Q1, Q2 over D squared. What do you know about force? Force can have two options in an electric situation. It could be or positive. It could be repulsive or attractive. Gravitational forces, you don't have to worry about that. Okay.
Negative gravity.
So if you look at when you do this force calculation, if you know your electric field. So this is why if you look at using this, you have an electric field which is newtons per coulomb. You multiply that by the charge that's in the electric field. The coulombs cancel out. You get newtons, which is what force is measured in. Okay? So there's two ways that you can determine force. You can use KQ1, KQ2 over D squared, or you can use FEC. Personal preferences, depends on what you've got. Now, here's the story. If you look at this next part of what's going to happen on question number 2. So the other way that you can look at voltage is that it's KQ over R. Okay? So again, if you look at the units, you've got newtons, meters squared over coulombs squared, times coulombs divided by meters. So this cancels out. You lose one of the coulombs. You have Newton meters per coulomb, which is what voltage is measured in. So when you get into part 2 of this lab, okay, listen to me very carefully. You're going to try and find the voltage at different points from a charge, and then you're going to have a situation where you're going to have like 2 positive charges or 2 negative charges. And you're trying to find the voltage like in between. So what you want to look at on this is that if you look at voltage in terms of KQ, and then if you factor out like the 1 over R1 plus 1 over R2, and you can go on and on and on. So as long as these two have the same charge, and the K is going to be the same, that obviously isn't going to change. So here's what I want you to see. And this is what we talked about yesterday, and this is the whole point of all the questions on part 2, is you're going to look at a 2-charge system. So I tell you, on part 2, you're going to clear everything off. You're going to start from scratch. You're going to have a positive 1 nanocoulomb charge, and then you're going to have a negative 1 nanocoulomb charge. And they have to be 2 meters apart. If you're not sure, you have a little tape measure. Measure out 2 meters, okay? These have to be on that grid 2 meters apart. So, then this turns into some calculations. You're going to, okay, hey, is there a point in the middle where the electric field will be 0? So keep in mind that you're going to have a negative charge and you're going to have a positive charge. Remember, how do you define the direction of an electric field? Based upon what a positive test charge is going to feel. If I put a positive test charge right there, what's it going to feel relative to that negative charge over there? Pulled or pushed? It's going to feel pulled in this direction. What's it going to feel from that positive charge? Pushed. Are both of those fields going to be pointing in the same direction?
Yes.
Yes. Fields are vector quantities. Okay? Now, if you have 2 negative charges, then could the fields balance out? That's the point of this. So when you answer these questions, okay, and I'm going to give you probably till about 2 o'clock. Work through part 2. You can always verify this, and this is the beauty of this program. So you're going to click and drag the dot sensor to verify your answer. Record your observations, okay? The whole point of part 2 is that I want you to look at what's going to happen between the electrical field and the relationship with voltage, okay? So I'm done. Stop that. Work through part 2.